Good day, everyone. Myself, Cyril V.S., research scholar from Department of Instrumentation, Cochin University. Today, I am here to present my research paper entitled Sol-Gel Synthesis and Investigation of Dielectric Behavior in Barium Stannate. The presentation is structured as follows: introduction, materials and methods, results and discussion, and finally summary. First of all, I would like to give you an overview of perovskite materials. Perovskite materials are a group of materials with general formula AbX3 having the same structure as the mineral calcium titanate. It is one of the most frequently encountered structures in solid-state physics, and it could accommodate around 90% of the metal ions of the periodic table that stand at the A and or B position. Such a feature provides the chemical tailoring of the materials via partial replacement of the cationic sites with foreign ions and hence modifying their structural, microstructural, electrical, and magnetic properties. Such a phenomenon gives rise to various complex types with peculiar properties and extensive applications such as superconductors, metal, semiconductors, insulators, dielectrics, and piezoelectric. Next, coming to our material barium stannate. Barium stannate belongs to perovskite group of compounds. In the cubic structure, the Ba2 plus ions occupy the corners of the elementary cell, tin ions at the body center, and the O2 minus ions at the phase center. Basically, it is a wide bandgap material with lattice constant A equal to 4.1163 Armstrong with space group PM3M. It also possesses excellent thermal stability up to 2000 degrees Celsius. Even though numerous methods are available in the literature for the synthesis of barium stannate, for the present work we adopted Sol-Gel method. It is because Sol-Gel possesses low processing temperature, high product purity, excellent chemical stoichiometry, and compositional homogeneity. Next, we will focus on the characterization aspects. The XRD shows the cubic perovskite phase and diffraction peaks of the samples were indexed. The grain size of the BaSnO samples obtained after annealing at 900 degrees Celsius and 1000 degrees Celsius are 28 nanometer and 34 nanometer respectively. The obtained results are very well in accordance with the JCPDS file of barium stannate. Next shows the X-phase spectra of as prepared BaSnO samples. The peaks at 781 EV, 796.7 EV representing the Ba3D 5/2, Ba3D 3/2 confirm the presence of Ba2 plus species. SN3D 3/2 and SN3D 5/2 peaks were identified at binding energy of 496.1 EV, 487.6 EV showed the existence of tin 4 plus species. The O1S spectrum centered at 529.4 EV and 532.8 EV indicates the presence of O2 anions in the samples. The Ba peaks at 771 EV, 793 EV, and other tin peaks at lower binding energy at 484 EV and 492 EV related to the presence of suboxides. Similarly, the X-phase spectra of BaSnO 6K 1000 samples are shown in the figure. 778 EV, 794 EV representing the Ba3D 5/2 and Ba3D 3/2 confirm the presence of Ba2 plus species. The tin SN3D 3/2 and SN3D 5/2 peaks were identified at binding energy of 484.3 EV, 492.7 EV showed the existence of tin 4 plus species. The O1 spectrum centered at 530 EV and 532.8 EV indicates the presence of O2 anions in the samples. The microstructure of the sintered pellets after dielectric measurement were observed from FESM as shown in the figure. Both BaSnO samples have a polycrystalline grain structure with granular morphology of different sizes. The figure shows that for BaSnO3 900 sample, the grain growth is not distinctive and the grains are isolated. For BaSnO3 1000, the collapse of adjacent grains take place and has a denser and uniform microstructure than the sample BaSnO3 900. And the results of EDS analysis conducted on pellets are shown in the figure 4A and 4B. EDS analysis confirmed the elemental ratio of BaSnO3 900 and BaSnO3 1000 is close to 1:1:3, and the presence of all desired chemical elements in the samples. The analysis confirmed the stoichiometry and chemical homogeneity of the samples. Let's now move to the dielectric part. The frequency-dependent relative permittivity measurements were conducted at various sintering temperature are illustrated in the figure 3.4. The observed high dielectric value in the low range of frequency is due to the contribution from phase charge polarization and orientation polarization. As frequency increases, the inability of dipoles to follow applied field variations results in the drop of dielectric constant. When the sintering temperature increases, the grain conductivity and the crystallinity of the samples are enhanced, leading to conductive behavior in the samples. Hence, the magnitude of permittivity decreases with an increase in sintering temperature. Also, the crystallinity leads to a large realization time for the charge carriers. High temperature sintering of perovskite oxide results in high oxygen deficiency, which causes an increase in conductivity. The table shows the comparison of the previously done works. For our work, we got 2476 relative permittivity for samples sintered at 900 degrees Celsius and a relative permittivity of 889 for the samples sintered at 1000 degrees Celsius. It seems that the origin of this giant dielectric constant is non-intrinsic, and the Maxwell-Wagner polarization effect caused due to the electrical inhomogeneity of the prepared sample has contributed to the dielectric anomaly. The Maxwell polarization effect occurs in ceramic materials comprising semiconducting or conducting grains separated by highly insulating grain boundaries. This will lead to the formation of asymmetric charge distribution in materials and contributes to the giant relative permittivity in ceramics. However, it is stated in literature that the reasons behind the dielectric anomalies are still under investigation. So finally, to summarize, barium stannous ceramics were prepared by the sol gel route. XRD showed that the samples have cubic structure. EDS and XPS spectra reveals the chemical state existence of desired elements for BaSnO samples. FVSM studies confirm that the samples have granular shape. Influence of sintering temperature on dielectric properties of BaSnO samples as a function of frequency were investigated. Maxwell-Wagner polarization contributes to the giant relative permittivity of the BaSnO ceramics. Then the references. Then finally, thank you.